You ever wonder what keeps the entire digital world from just falling apart? I mean, we're talking trillions of lines of code running everything. Well, it turns out there's this hidden rulebook, a kind of digital contract that manages the incredibly delicate dance between the hardware in your hand and the software on its screen. So let's dive in and see how it works.
All right, so here's our game plan for this explainer. First, we'll get into the core reason why modern tech fails so spectacularly. We're calling it the multi-speed problem. Then we'll look at the solution, forging the digital contract. After that, we'll check out the universal rulebook that makes it all stick, see these contracts working in some super high-stakes situations, and finally, we'll see how this is all building a safer future for all of us.
Okay, so let's kick things off with the problem itself. And this isn't some abstract, theoretical thing. No, this is something I'm willing to bet many of you have experienced firsthand. And it is beyond frustrating. Oh, you know that feeling, right? That pit in your stomach when a totally normal, routine update finishes and your $1,000 phone is now a useless brick. It feels so random, so unfair. But it's not random at all. It's actually a symptom of a really deep structural conflict, right at the heart of how we build technology today.
So what's really going on here? Well, it all boils down to this. The physical hardware, the firmware that makes it work, and the software apps we use, they're all evolving on completely different clocks. They're built with different rules, different constraints, different timelines. And that fundamental mismatch, that's where the chaos comes from.
This table just lays out the conflict perfectly. On one end of the spectrum, you've got hardware. We're talking development cycles measured in years. You're constrained by the laws of physics, by global supply chains. It's slow. In the middle, you have firmware. That's the bridge, iterating over months. And then you have the software world. Here, things change in seconds. It's all about agile, DevOps, constant updates being pushed out automatically. These three worlds are on a permanent, high-speed collision course. So how do you stop that collision? Or at least, how do you manage it? Well, we have to move away from just hoping things work together and start proving they will. And that's where we get this idea of forging a digital contract. Now, the main battleground for this contract is something called the hardware abstraction layer, or HAL. You can think of it as the demilitarized zone, the border between the physical world of silicon and the purely logical world of software. For decades, the rules for crossing this border were based on informal, handshake agreements written down in documents. And this slide really gets to the heart of the shift. Those old handshake deals were written in plain English, which, as we all know, is full of ambiguity and open to interpretation. Formal contracts, though, they're based on cold, hard mathematical logic. You can't really misinterpret an equation, can you? And this is what's so powerful. It lets us stop relying on slow, manual testing and start using machines to automatically prove that the contact hasn't been broken.
And just so you know, this isn't some academic fantasy. This is being used right now by huge companies like Amazon, Intel, and Microsoft. They use incredibly powerful tools to build these contracts. For instance, some tools model how a system behaves over time to make sure some random event doesn't crash everything. Others are all about structure, like putting puzzle pieces together, defining the rules for how everything has to fit. And finally, some act like a funnel, carefully refining big abstract ideas down into concrete, proven code.
Okay, so you have a contract. Great. But it's totally useless if nobody agrees on the language it's written in or if everyone has a different version of it. To make it work, you need a universal rulebook, which means you need a shared language and a single source of truth. The shared language is something called Semantic Versioning, or SemVer. Now, it looks pretty simple, right? Just a major.minor.patch number. But the real magic here is that the numbers themselves have meaning. A change in that very first number, the major version, sends a clear, unambiguous signal to every other part of the system. Warning, something fundamental just broke. Pay attention. And you can see here how SemVer works like a universal translator across the whole system. Let's say the hardware team changes a pin's voltage. That's a huge breaking change. That forces them to make a major version bump. That, in turn, forces a major version bump in the firmware's digital contract, which then signals up to the software that its public API has a breaking change. Everyone, at every level, is suddenly speaking the same language of risk. So that's the language. The second part of the rulebook tackles this classic, almost philosophical problem, the massive gap that can exist between the system you designed on paper and the system that's actually running out there in the real world. You have to be able to manage both. The way we solve this is pretty clever. We just split the idea of truth in two. Think of it like a building. First, you have the definitional truth. This is the architect's blueprint. It's the intent of what the system should be. And it lives in version control systems like Git. But then you have operational truth. This is the inspector's report. It's what the system actually is, right this second. To have a truly reliable system, you need both the blueprint and the inspection report.
All right, theory is great, but does this stuff actually work in the real world, especially in high-stakes environments where you absolutely positively cannot fail? Let's take a look. Imagine a live TV studio during a major broadcast. You've got literally thousands of video and audio feeds flying around a network. It's pure managed chaos, and failure is just not an option. To prevent disaster, the whole industry relies on a protocol called NMOS, which is basically a live, dynamic digital contract for every piece of media gear. So how does it work? Well, NMOS basically forces every device to describe itself in the exact same structured way, from the physical box on the network, the node, all the way down to a specific flow of video. Because everyone is using this shared data model, this contract, a controller made by Sony can instantly discover, understand, and route a signal from a camera made by a totally different company. It just works. Now let's swing to the other extreme, critical infrastructure. Think power plants, water treatment facilities, factories. A lot of these places are running on ancient protocols from the 70s and 80s that have absolutely zero security built in. You can't just rip them out, so what do? You wrap them in a modern cryptographic security contract. And a security contract like this has to protect the hardware through its entire life, from the moment it's just a design where malicious circuitry could be slipped in, to when it's sitting in storage where its secrets could be stolen, all the way to when it's up and running, where it can be attacked with things like voltage glitches to make it mess up. The contract has to defend it at every single stage. And you might be thinking, well, adding all that security must really slow things down. But get this, using modern super lightweight crypto, we can encrypt and authenticate commands on these old systems in 4.8 microseconds. That is ridiculously fast. It's more than fast enough to secure a protocol in real time without ever disrupting the critical industrial process it's controlling. Okay, so let's pull back and look at the big picture. What does all of this mean for the future? Well, it's about a really fundamental shift in how we think about building the world around us. And this is maybe the most important takeaway. Adopting digital contracts isn't just about using a new tool or a new technique, it's a cultural change. It forces engineering teams to think about and build in reliability, safety, and security from the very first day of a project, instead of trying to sprinkle it on at the end and hope for the best.
This new approach, this new culture, even has a name: DevSafeOps. It's the practical, real-world application of everything we've talked about. It takes all those important safety and security requirements that used to live in some dusty binder on a shelf and embeds them directly into the fast-paced automated development pipelines that teams already use every day. Safety becomes a continuous automated process, not an afterthought.
Which leaves us with one final, pretty big question to think about. As our entire world, our cars, our hospitals, our power grids, becomes run by software, those old handshake deals just aren't good enough anymore. So the question is, are we actually going to engineer systems that we can prove are trustworthy? Or are we just going to keep closing our eyes and hoping for the best?